Hello, I am Bryson Hedrick. This is my presentation on an introduction to tensors for Math 2240. Tensors are used to describe curved spacetime. The purpose of Einstein field equations involves the use of tensors. The picture is supposed to show the differential geometry of general relativity, GR. Tensors can be found in applied fields such as geology or engineering. First, I will relate vectors from Introduction to Linear Algebra and how it relates to everything we have learned in the course. Next, I will talk about how index notation is used to describe tensors and put multiple operations into a compact form. Then, I will talk about some types of tensors which will be covariant, invariant, asymmetric, and some anti-symmetric and symmetric. Lastly, I will mention spe- two specific tensors and their applications. Tensors relate to everything that was mentioned in linear algebra this semester. Vector spaces span matrix multiplication, cross product, and the dot product are some of the operations used with tensors. Determinants are used in some cases, and the identity matrix sometimes is utilized. Matrix and vector operations such as addition, subtraction, multiplication, transpose, and more are important for describing vectors. For describing tensors, transpose would be one of those just for the matrices. Figure 2 illustrates span and figure 1 shows systems of equations. What is a tensor? The rank is determined by the number of free indices. Free indices occur one time. Matrices are used to describe the vectors with multiple components. Tensors use vector space and transformations. Tensors use transformations similar to linear transformations to describe the change in a coordinate system by using basis vectors and are invariant in different coordinate systems. The number of free indices determines the rank of a tensor. By understanding basis vectors, unit vectors, coordinate systems, and linear transformations, tensors can seem slightly more intuitive. A scalar is rank 1, one component is rank a scalar is rank 0, one component, vector is rank 1, and a vector has magnitude with one direction of I hat, j hat, k hat, and a dyad is rank 2 with 3 components. Dyads have 2 directions, so it would be 3 to the 2, which is 9 components. Components are the dimension to the rank. Just remember that matrices are multiple vectors and tensors are using transformations. Index notation has been used before in linear algebra and is not usually recognized when doing determinant. And it is not usually recognized. When doing determinants, the cofactor expansion C lower index ij to equals -1 to the I plus j multiplied by the determinant of a lower index ij is commonly used. Also, the dot product of two vectors can be represented in a similar way. You can go from k equals 1 to the number of columns of A and of A and then multiply A, Ki, and B, Kj components of each vector in the lower index. We need to distinguish between inner product and dot product with tensors. Tensors will be using higher dimensions, and the dot product only works for Euclidean space. The inner product will therefore be slightly more useful when using geometries that could involve the use of different coordinate systems and vector properties. Figure 8 shows the distinctions in Euclidean and Riemann geometry. And then figure 7 is showing the Einstein summation notation. Kronecker delta function. If I equals j, such as I equals 1, j equals 1, the function will equal 1. If j not equal to I, such as I equals 1, j equals 2, the function will be 0. It is a variant of the direct delta function used in physics. From linear algebra, we know if two vectors' dot products are 0, they are orthogonal or at 90 degrees or pi over 2. The basis vectors E subscript I dot product E j are orthogonal vectors since they have been normalized or their magnitudes equal to 1. They are orthogonal vectors since they are both orthogonal to each other and their magnitudes are 1. The orthonormal basis rule is related to the Kronecker delta. It shows that EI dot EJ equals delta IJ, along with two different vectors having a dot product of 0. If the same vectors such as EI dot EI equals 1, they are unit vectors. If you did E1 dot E1, it would equal 1 and delta 1, 1, while E1 dot E2 would equal 0 or delta 1, 2. When a tensor has the same components in all coordinate systems, it is called a constant or numerical tensor. It is a tensor of rank 2 since it can be thought of as an n by n matrix, which is an identity matrix. So these both involve orthogonality and orthonormality. Another related tensor using the index notation and similar to Kronecker delta is the Levi-Civita tensor. The Levi-Civita is rank 3 and can be represented as a summation or a determinant from the cross product. When using the Levi-Civita, it uses orthonormal basis vectors similar to the Kronecker delta. It will rank 3 in Euclidean space with 3 dimensions. The cross product C of A cross B is a determinant that can be calculated with the use of Levi-Civita. The identity of the cross product can be shown by summing each component in the values of I with the basis vectors. As I said on check by sum. Einstein summation convention was utilized in Kronecker delta and Levi-Civita. It is the use of indices and summation to generalize equations. It helps show all the components in operations such as dot or cross product. It uses dummy variables as a method of summation. It is related to the index notation we mentioned before. The Levi-Civita symbol uses the properties of permutations to work as a function. The pseudotensor or tensor density is because the tensor changes by a scalar from the Jacobian matrix. In calculus 3, the Jacobian matrix is a determinant that helps change in between coordinate systems such as spherical and cylindrical coordinate systems. The Levi-Civita symbol uses the properties of permutations as a function. The pseudotensor tensor density is because the tensor changes by a scalar from the Jacobian matrix or determinant. Also, according to the pseudotensor, the Levi-Civita does not change in different coordinate systems. The Levi-Civita does not have a preferred basis and is not within the set of -1, 0, 1. Tensors have to be the same in all coordinate systems. Its transformations are created by the determinant of the transformation matrix, while a tensor will not use it. If their basis vectors have to change, the tensor cannot be the same in all coordinate systems. In calculus 3, the Jacobian matrix is a determinant that helps change between coordinate systems such as Cartesian, spherical, cylindrical, or polar. Figure 16 is the Jacobian determinant. Figure 15 shows the computed Jacobian determinant for Cartesian to spherical coordinates. And as you can see, the permutations with the Levi-Civita symbol. When using the change of basis, it helps to use generalized coordinates. There are so many transformations occurring in tensors it will help when coordinate systems switch. Covariant tensors have specific properties and are defined and can be defined as the gradient as shown as the picture. The gradient is from calculus 3 and takes the partial derivative of x in the x hat direction, the partial derivative of y in the y hat direction, and the partial derivative of z in the z hat direction. The lower index is utilized and is the covariant derivative. The covariant gradient. It is a covariant derivative operator. Invariance in tensors does not mean it does not change under basis transformation such as determinant, inner, and outer product. Contravariant tensors are similar to covariant tensor transformations. Contravariant tensors have raised indices. Covariant and contravariant tensors are useful when describing these transformations. Lastly, tensors are invariant in coordinate system transformations. This is important in linear algebra because basis vectors are the composition of coordinate systems. Basis vectors define a coordinate system. A symmetric tensor's indices can change places and equal each other. And antisymmetric's lower indices are equal to it if the lower indices order is switched and it is negative on the other side. The Kronecker delta is symmetric while the Levi-Civita is antisymmetric. Tensors can seem very hypothetical. However, there are many applications. For example, Einstein field equations utilize tensors, and the metric tensor shown here is one utilized in Figure 20. Figure 22 is a representation of the stress tensor that is used in civil engineering and geology. Specifically, Cauchy's law and Moore's law utilize tensors. Thank, thank, thank you for your time today.